Thanks for coming. My name is Tom Oteki, and I'm the Director of the Academy of Data Science, and it's my pleasure to introduce our speaker today. But before I do, I'll mention to everyone we're recording the session and probably do that in the future as well, but we are recording today. So our speaker today is Oliver Schabenberger. Oliver is a professor of practice in the Academy of Data Science. He got his PhD from Virginia Tech in forestry and a master's degree in statistics. He then went on to Michigan State University, where he was an assistant professor. And then shortly after that, he came back to Tech for his first trip back to Tech, where he rose to a tenured associate professor in the Department of Statistics. In the early 2000s, Oliver moved to SAS Corporation, the statistical software company, where he was a distinguished fellow and eventually rose to be the chief operating officer of the company, which is the number 2 position in the corporation. He left SAS in the early 2000s, early 2000s. And early in 2019 or in 2020 is when he left. Went to be the chief innovation officer at this Single Store Corporation, which is a startup in Silicon Valley. And then in early 23, I became acquainted with Oliver and had the good fortune to snag him to come to Virginia Tech, which is where he is now. As a professor of practice in the academy. Oliver's the author or co-author of 3 textbooks in statistics, and he is a fellow of the American Statistical Association. So it's my pleasure. Yeah, Oliver, the floor is yours.
Thank you, Tom, and I'll try to live up to the introduction.
Yeah. You better. He got dressed up for this.
Yeah. Well, I got dressed up because I now fit into those clothes again that I was wearing years ago. I want to talk to you today about model interpretability and explainability, because it's something I got interested in when I was involved in data science and building models, creating more complex models, but also because when I worked at SAS, customers kept asking us about that. How do I actually interpret this? And what does it mean? What does makes a model tick? What are the consequences of using this? And I'm teaching Stat 5526 this semester, and I added this as a module in the class because I think it's really, really important for us to understand what that is. We go through a process of more and more automation around modeling, and what I'm seeing now is actually automation of these explainability tools. So we're doing automating on top of automation, and before you know it, you don't even know what you're doing, you just get an explanation. And there are pros and cons with these methods, there are pitfalls, and you should be aware of them. Now, Abby talked in model interpretability. Starts with this. This is obligatory. You all know that cartoon, but it's essentially what it's all about. There's an input to something, something happens, and something's produced on the output. And this is my 30-year career in data in a nutshell. This is all I've learned. And everything we do can fit into this schema, right? There's some input, stuff happens, good stuff, bad stuff, but some stuff, and then there's an output produced. Now, interpretability and explainability, you will see them used interchangeably a lot. You hear about explainable AI and interpretable machine learning. They are actually different things, and I make a point out of them being different, and so that we have an understanding of when we move from interpretability, which we would love models to have, to explainability, which is often the best we can hope for. So interpretability is a property of a system that can be made understood. Can you make something understandable and know how it works so that you can answer the question, if I turn that knob on the input, this will be the result on the output. It's interpretability, models that have that features. Decision tree, simple linear regression, all of that. A deep neural network, you cannot tell me when you change the input or rotate an image by 45 degrees, what the impact on the output will be from looking at the algorithm. You have to experience and do it. So explainability is about looking at the output side and say, can I figure out how the system came up with that decision? This is less than interpretability, and it's often all we can hope for. So most of the tools we'll talk about are going to be tools about explainability, because if you have an interpretive model, you have no problem. So why the discussion right now? Because interpretability and the transparency are on a collision course. We get more and more requests for being transparent in our analytic assets, yet most of the things we do don't aid interpretability. Highly interpretable things like decision trees tend to be really poor performer in practice. So the things we do to improve performance, like assembling them in a random forest, they take away interpretability. Adding inputs to any model reduces interpretability. And so models become more complex and interpretability goes down. At the same time, we're asked to be more transparent. We have to explain those assets to people who are not domain experts, not statistical experts or machine learning experts. And organizations are starting to look at models as sources of risk, financial risk, operational risk, reputational risk. What is that face detection algorithm goes bad on us? So if I have a risk, I need to manage the risk. In order to manage the risk, I need to know what the risk factors are. And maybe I even buy insurance in the future for the models I deploy. So we need to be able to communicate and explain what those models are. If you look at legislation and regulation, everybody working in financial services will know that if you make a decision about credit, no matter what tool you use, you are required by law to explain that decision to the recipient. So you use an opaque algorithm somewhere in this decision chain where at the end a loan is being approved or denied, and you cannot explain a step, the entire decision chain gets contaminated. Are you familiar with GDPR, the General Data Protection Regulations of the European Union? It's really landmark legislation in data privacy and how to use analytic assets, how to use data. It's a couple of years old, and people sometimes say, yeah, but it's in the EU. Well, I'm a dual citizen, and so if you do anything algorithmically about me, I'm covered by GDPR. There are several rights in there. For example, one is the right of explanation. That means, here's the text from the regulations. You have the right to obtain an explanation of the decision reached and to challenge the decision. So we need to know what it actually means to explain a decision. So you have a model that has 20 inputs, 200 inputs, 1,000. Do you need to go through all 200 or 1,000 and say, okay, well, your loan was not approved because, or an algorithm that is used in assessing punishment in criminal court because of this feature and that feature? No, actually not. You have to be selective, and you can you focus on the most important ones. But what are they? What are those most important features? So here's a set of data that I use in my class. Theophylline concentration or some other concentration. That's just its concentration as a function of time. It could be the drug being absorbed and eliminated from the body. It could be my attention span watching Netflix, right? It goes up. And after a while, so how do you model this? Does it matter?
We're at that point in your talk right now. We're peaking.
Thank you for coming, Dave. So here are three model choices. Dave choose the simple linear regression. Actually, it's probably possible out here, but that's what we call in technical terms. That's barf on a stick. You wouldn't want to go with that model. Pretty obvious. But there are two others. The black line is a pretty smooth model. The blue line is a low S fit. From a mean prediction error perspective, the blue line may actually be the superior line. But does it matter which one I choose? What if I say this is a very highly interpretable model, whereas the low S is not? So interpretability as an attribute to judge the quality of a model is really, really important. And depending on the context, it may be one of the most important attributes that unless the model is interpretable, you may even go there. Don't think of this as a all or nothing thing. A model is not either interpretable or not interpretable. It is a continuum, depending on how complex you make things. Even starting out with a simple linear regression, you add progresses to it, the model becomes less interpretable, it becomes big, you use a lasso regularization, you take interpretability away, rich even more so. So we're somewhere on the spectrum. But pretty much everything we do, that's the message here. This is what I call my mind map. I have for every module in my classes, I have mind maps that help the students understand how I organize stuff. This is how my brain works. I hand it out to them, they get the source file so they can move it around and mess with it to put it into the shape that their mind works, conceives this material best.
Very complex model to interpret.
But it's very interpretable. On the right, on this side is levels of interpretability, and we're going to talk briefly about intrinsically and interpretable ones, but then we move on to, this is where it matters, the explainability tools. Models that are intrinsically interpretable, you can look at the model, and just from the very structure, you don't need to know anything about the values of the parameters. You can tell me how it works. This is the most interpretable models. Linear regressions are in that a model. A lot of computational models we build are domain-specific models where every quantity has a meaning in the domain that we're working. Interpretive model are the ones where we look at the parameters, we change them, and we say, oh, this is how it works. You change that feature by 1 unit, the response is such and such, and the coefficient would tell us, for example, in a linear regression. As soon as you go beyond that, less interpretable than that, explainability is the best you can hope. And there are two classes of explainability tools. The one that is most popular and gets a lot of attention are the model agnostic tools. Because there, it doesn't matter how you derive the model underneath. You can apply to anything, whether it's a neural network or a random forest or a gradient boost. These techniques apply everywhere. So they're very popular right now. And then there's some model-specific tools. I've worked with colleagues at NC State on trying to interpret neural networks for language, natural language understanding, very specific networks. But this is really where the action is. Within the model agnostic tools, there are two types, local ones and global ones. The global ones try to understand the model as a whole, across all observations, all inputs. And the local ones, they go one observation at a time. So for example, surrogate models is an approach where you fit an interpretable model to the predictions of a complex model. So you have that neural network produce predictions, and then you use a decision tree to explain them. So that's my reaction too. That stuff is real. And stuff is being automated, right? So imagine where you have this complex analysis. You build a model with hundreds of thousands of parameters underneath, and the output will be a decision tree with 4 nodes. And this is how you convey that information. You can see the danger in doing it. Whereas a local surrogate model will fit a separate model for every observation. You'll see the term Shapley on here a lot. Shapley values and the Shap method is probably right now the winning method in explanation, model explainability. I like him. I think you have a lot go for them. You have both local and global interpretation. You can aggregate the local ones to the global ones, which is not always true. You see that stuff about feature importance, partial dependence. Shapley has versions of that for all of it based on these kind of the Shapley values. We're going to go through how to derive the Shapley values because that's another black box for many people that don't know how they come about. And I find it ironic if we use something we don't understand to explain something we don't understand. This over here is really, really important, that note. And that's a really danger of these methods. Imagine you have, again, let's go back to a very complex model with hundreds of inputs. And now we're choosing 2 particular inputs with a surrogate model to explain how the model works. There's a danger to jump to causation, say, okay, this is what really matters. This is what really happens. And we never should do that because all we're going to do with these tools is explain what drives the model, not what drives the process to generate the model. If you build a crappy model with crappy features, these tools will tell you which crappy feature is important for the model. It's not necessarily important.
Oliver, in regard to the local methods, you said you get an explanation for a single observation. So I have this very complex model. What is the nature of the explanation that I get for this particular
So
observation?
you have to choose an interpretable model. Usually some form of regression, say do a simple linear regression. And then at each data point, there's going to be a permutation, perturbation of the data locally with a kernel function. And then you fit the local regression model to that local perp data at that point. And your interpretation is now the intercept and the slope of that regression. And then you move to the next data point and then you repeat the process. So there's a lot of things that go into it. We'll talk about it. I have this called LIME, local interpretable model explanation. How you choose the neighborhood, how you perturb the data, what kind of local method you use, which variables you use, how many you use. All those decisions affect the quality of that local model. Surrogate. Decision tree, one of the most interpretable models there is. It's so simple. You have either events and non-events. They have some biological characteristic, and it tells me exactly how a decision is made. Also performs typically very poorly by itself. AlexNet, an example of a non-interpretable model. The difference between how does a model work and what does it do? I can explain what it does. First layer is a convolutional layer with 96 kernel and an 11 by 11 convolution stride 4. I can tell you what pixels go through when they do this. But I cannot tell you what happens to that image when it comes back out on the other side, because these 96 kernels are themselves learn from the input. It's opaque. But this is a non-interpretable model, although you can explain what it does. So explainability tools are the only thing we can apply to these things. For the rest of what I'll talk about, it's actually largely based on this great book that's online. I'm going to post the slides. So you have all the links. I'm also posting the R markdown of the analysis we'll do. This is also Chris Molnar is the author of the package IML in R that I'm using for this. It's a lot of cool analyses that that package can do. Pretty much anything we'll talk about is covered in there. Okay, so now we'll talk about the center column here, the model agnostic tools. Before we go into the first method, watch out for the assumptions. These are not assumption-free methods at all. And one of the ones that rubs me wrong the most is the assumption that what is in the literature is called features are uncorrelated. Statisticians say, okay, they're not stochastic, are they stochastic? What they mean is the input features of your model can vary independently. And that is a horrible assumption. So imagine you're modeling home prices and you have two inputs, the number of bedrooms and the size of the living area, right? Bedrooms number varies from 2 to 10, living area from 1,000 to 6,000 square feet. So these are explainability tools that have that assumption will combine input values and will explain how the model works by predicting a house with 2 bedrooms and 6,000 square feet and a house with 1,000 square feet and 10 bedrooms. These things don't exist. But this is the foundation of the algorithms when they go through possible combinations. It's important to know almost all these methods make that assumptions. Anybody familiar with partial dependence plots? One of the first things that folks look at. The idea is I have all these features. I want a global method, but I can possibly consume a p-dimensional space when p is bigger than 2. So what I'm going to do is I'm going to pick out a couple of features that I think are important. And then I'm going to look at the predictions or classification for those features, average, not condition, averaged over all the other features. So essentially what you do is you're separating the features into 2 sets. One is called the set of interest. The other one is the complement set. There's only 1 or 2 often in the interest set. And then you're fixing a value for a feature in the interest set, and you're running over the data, averaging over all the values you observed. So this is why you fix the number of rooms at 2, and you sum over all the other variables, and this is how 2 bedrooms gets combined with 6,000 square feet. Here's an example from Molnar's book. The data that comes from his book, I did a different analysis. Bike sharing data in Washington, DC. This is the number of bicycles shared per day. And partial dependence plots for 3 variables. Temperature, humidity, wind speed. There are 13 variables in this model. So when I look at temperature, it shows me, the average prediction will go up till about 20 degrees centigrade and then drop. That makes sense, right? If it gets too hot out, people don't want to choose the bicycle. They use some other modes of transportation. Similarly with the humidity as it goes down, or it gets really windy, and you have fewer riders. But again, there's an important assumption here that if I look at 10 degrees centigrade, that I can now average over all the data points in the data set. And this is data from every day in the year. So there are days in the summer that now say, okay, if I have 10 degrees centigrade in the summer, then what is the number of bikes? It will be a prediction that goes into that average. And it's a data combination that can never happen. But it shows you the average prediction as a function of the value averaged over all the other variables. There is a local version of that called ICE plot, individual divisional expectation plots. And what you do there is you simply don't average all those. That's some we saw. You display them for each individual observation. So here are the ICE plots with the PDP, the partial dependence plot in. So these are the 731 lines, many observations in here. And if I average them out, I get these yellow lines, which you saw on the previous plot. Similar issue. So if you look at the top line, let's say this is one observation. It has its set of covariance values. Now I'm holding the covariance fixed. And I say, let me predict it at 0 degrees, 5 degrees, 10 degrees, and you go through this. This could be an observation from mid-August, and you're predicting at freezing temperatures, and this will be the value. Same problem with, features not varying independently. But one of the advantages of that plot is if you have interactions, this will show it. Whereas when you average across interaction, you might mask them, and the partial dependence plot might not show. So then that is a popular display to show them together. Unfortunately, if you have more than a couple of hundred observations, it gets very busy and difficult to interpret. A nifty variation of these ICE plots is when you center the plot at a particular value of a covariate of interest. So here it's centered at 15 degrees centigrade, and you can see the predictions, how they should shape up below and above that for all observations. Recommend to put a rug plot on there so you see the density of the values, so that you don't overinterpret the really sparse region where you don't have much data. I'll give that example already. The next set of global explainability measures are the variable importance plots. In the previous 2 plots, we actually had to decide which 3 variables I were looking at out of 13. That's the first decision we made. So why are temperature, humidity, and wind speed the important ones? Well, there are tools like the VIPs or FIPS, the variable importance plots, to do that. If you work with regression trees or classification trees, you're familiar with importance plots, feature importance plots. But there you plot the importance of a variable as a function of some objective criteria, like the drop in mean square error or the increase in node purity. These are different. These are based on permutation. So I'll take my data, say I have 4 variables. Now I'm randomly permuting one, just reassigning the values. And by that, I break the relationship between the feature and the target, what I'm predicting. And so within that permutation, now I'm predicting all the observations. And I see how much a criterion like accuracy or mean square error changes between the permuted and the unpermuted data. And the rationale is, if I have a feature that really matters to the model, and I permute its values, then whatever criteria I look at will go through a large change. Like the mean square error will increase a lot, or the accuracy will go down. But if the feature is unimportant, it will not be accurate. And then you make these plots, So there's 10, I did 10 permutations on each feature. So you have to permute the data, each feature, predict everything. And so these things can become a little computational intensive, but they're also easily parallelized. For the bike sharing data, number of days since 2011 was the most important thing. Now, the longer this thing has been in place, the more people are using the service. Next to that, temperature matters. Next to that, year matters. Wait. Year? We already had days since that's the same information. As the number of days since 2011 increases, the year increases. So there's again a correlation between these. I measured it with a mean square error, and the way I interpret this, the center at about 15. If you were to remove the relationship between days since 2011 and the number of bike riders, your mean square error would go up 5 units.
The year is the year that data were collected from.
The data is collected on daily basis. So if you take the date, the year, a month, the day component to it, so that is the year. Okay, we briefly touched on surrogate models already. Here the idea is I have a complex model I want to explain. So let me find a very simple model that's interpretable. Decision tree, regression, linear regression, something. And then I'm just going to fit that model to the predictions of the black box. So if I have just an API, I can shoot questions to and get the predictions. Then I could build up such a model that then models the black box models prediction. And you have some measure that tells you how close you are, how close the predictions of the black box are, and how good your predictions are, and at some point you say, hey, good enough. Now I'm going to just look at the surrogate for the patient. If the target is qualitative, it's some form of confusion matrix that is used, and if it's quantitative, one tends to compute some R² style measure. Y hat star is a prediction from the surrogate model. This is a prediction from the model you try to study, and this is some R² style measure on how close you are. And this is one of the problems. When are you satisfied? Is an R² of 0.6 good enough to replace the black box and use the surrogate as the interpretation? Does it have to be higher? So here's an example from a data set that comes with the mass library in R. It's old data from 1960. It's about US crimes. The data has been, even the R documentation says unknown scaling, the variable sign of scale you don't know, but so I don't want to overinterpret this. Also, there's log transformation and everything. But what I did here is an ensemble method, Bayesian model averaging. So I have 115 models in the ensemble. So that means a prediction will be a weighted average of 115 individual predictions. This variable M shows up in 97% of all the models. Add some value level of education shows up in every model. This one, M.F, shows up in only 7% of them. It'd be interesting to use a surrogate and say, tell me what drives these predictions. Because I need to explain to somebody how, what matters for crime. So I did a decision tree. And I don't want to overinterpret the names of the variables. That's where you really get in trouble. That's because this is old data and the scaling is unknown. And this would suggest to understand the predictions of the model, the most important thing is some level of police expenditures. Then on this side is population metric. There's some non-white ratio of male and females, 0.78. Yeah, but what if I don't want to talk in my explanation about these variables? It's kind of uncomfortable to talk about. Let's try this. There's a nice decision tree. Has only 5 nodes. Yeah, and I dropped some of those uncomfortable variables out. I like this better. It has an R² of 0.66. No.
I have a quick question. Isn't R² only meaningful if the 2 points have the same mean, right? So the same baseline. So I'm asking, can we assume that the neural network produced the same mean as the tree later on?
Well, if they are equally bias, they should agree on average.
Okay,
Right.
so then the R squared by construction is meaningful in that. Okay.
I think, given that, what is the level where you're comfortable in saying, I'm not comfortable with the method at all, so the question of the R squared.
I'm comfortable demanding that we spend more money in the police enforcement. That's what that model.
But you see the danger of this, how the selection of which things you look at will drive the explanation and it will drive the narrative.
It's funny if people think about it, right?
Now, there's a local variant of this and has a cool name and you hear that, you hear about it a lot. Not, I don't think it's all bad, right? But let's work through this. So you don't just want to have one model to give you explanation for a really, really big complex model. Well, let's localize. Let's try to come up with a simple model to explain each prediction from every observation. So if you have 1 million data points, you have 1 million new models. And you do this by looking at the data in the neighborhood of the prediction points, then perturbing it. Some random, usually if it's adding some Gaussian random noise to it. Pretend this is some local version of the data, like a tangent approximation, fit a local small model to it, and then stop them. That's called LIME, local interpretable model agnostic explanation. An interesting aspect of that, though, is you don't need access to the actual data underneath. You don't need to have the Y values of response. All you need is a prediction. So some methods actually, like Shapley, require you have access to all the data, inputs and targets and everything in order to calculate the explanation. So if you were in the business of developing services that explains other models, which you don't have access to the data, this might be an option for you to do.
So Oliver, in that sense, it seems like you would need to know what the inputs were to say what the neighborhood was,
Yeah.
right?
You need,
So you need that.
You need some form, but you don't. If I tell you the input is age and other variables, you can come up with values for the input without knowing exactly what the inputs were in the analysis.
All right, so I have to have access to the model itself.
But for example, if you do a feature importance with permutation, you actually have to permute the actual data. You need access to everything.
But maybe you said this before, but your surrogate model probably already has some error as well, right? How does that feature into the whole?
You have to make a judgment call how comfortable you are with the proximity of the surrogate predictions to the actual predictions. And I can't make that for you. I'm not comfortable at all.
Right. No, I was just trying to.
No, you're exactly right. I mean, think about, again, I think what I find troubling is I have the true values, right? And now instead, I'm using the predictive values that contains errors that actually is not necessarily good for a proxy for the true values. Right? That the whole problem is, why do I just fit the true model to the true values, right?
The black box model would be a really, really great model, and it's just complex. That's one thing, but the underlying model could be a really, really poor model. Where it could be working really well for parts of the data and really poorly in other parts of the data. And you're now trying to get an approximation to a poor prediction. Try to get close to that. But what are we gaining? We're explaining a poor prediction with variables that are more easily to understand.
Just for clarification, are these all within sample prediction or for a holdout sample? Because then that changes the equation.
That is a good question, and that's a debate on whether you should apply these methods to the training data or test data. So for example, feature importance. If you have total garbage features in your model, the feature importance plot should say you're not important. But as soon as the model picks up something from that variable, something spurious, it will show up as in the feature importance with a non-zero value. If you were to use the test data, it would show up with 0. So they're telling, but it's the argument is almost using on both because they're telling you different things. If you want to know, is my model susceptible to something? What are the things, the signals it's seeing you want to apply to the training data? If you want to answer the question, does that variable actually really matter for the predictions? You want to apply the test data. So in practice, this is how LIME unfolds often. You have to check the software. It's really important because they make so many assumptions on how this works. that they have an incredible impact on the outcome of the analysis. Use linear regression, add some random noise to the inputs. Then you have a kernel of, use a Gaussian kernel with some fixed bandwidth that determines the neighborhood. And you have to, look at the documentation, how you can change that. You pre-select the number of inputs in your interpretable model. So if I say P star is 2, I will get at most a multiple linear regression with 2 parameters. And you select it at front, and then the algorithm finds some way to match your local model, either the regularization parameter in lasso or some variable selection. What I found, once you select the variables and it picks those are the same variables that users throw out. It doesn't repeat the variable selection in other places. Quick example, then I want to move to Shapley. So I used the Boston housing data set, also an older data set, comes with the Mass library, but it's used a lot in data science courses. I used the random forest 50 trees and 13 predictors to predict the median value of a home in the Boston suburbs. And then I asked for a Lime interpretation for the first observation. This is a local method. So I asked for observation number 1 and said, these are the 2 variables that explain the prediction. The number of rooms, and this is some variable of status. So the coefficients in the regression didn't give me the intercept, the coefficients, and here are the values of the variables. So 3.03 times 6.5. It's the effect. It's the effect force for the number of rooms and a negative effect for the status. So then you can put this on a nice graph and says, the model, the random forest predicted 24.75 and the local model predicted 25.95. So what am I going to do with that? Is that closed? Am I happy with this? And this is the effect force of the first variable, and this is the effect force of the second variable. And if you add them up plus the intercept, you get the total prediction. And this will happen at every observation you ask.
So what does the 24.75 mean?
It is a prediction from the black box model.
Yeah, but what
Median value of the home, I think in some units of $1,000.
some value. Okay.
And now that we've seen this idea of effect force of an attribute, it's a good time to talk about the last method. And this is really, really fun. Okay, so I think this is the one that's most grounded in theory, over decision theory, and some very nice properties. One big drawback, it's really complicated and challenging. Exact solution is actually pretty much infeasible unless you have a very small number of parameters. But it doesn't stop us from using this. There are a lot of approximations that are being made. There are implementations for specific kinds of models where you can take advantage of parallelism. So they are becoming very, very popular. But in order to understand SHAP, which stands for Shapley Additive Explanation, you first have to understand Shapley values. Really, really cool. The idea came from a game scientist I think in the 50s, who asked, if I play a multiplayer game and there is some payout, some gain of having played the game, how do I fairly distribute the payout among the players of the game? Who should get how much, depending on their contribution? And now, how does this map to a statistical model or machine learning model? Well, the game we play is we want to make a prediction or a classification. The players of the game are the features in the model. The coalition of players is some collection of features. So not all the players may be present, and some, maybe if somebody didn't play this weekend, but they still contributed to the game overall. So there's going to be some payout coming. The gain is the difference between a prediction and some form of a baseline. Could be the average, could be a model without parameters or without inputs. And I want to distribute the gain among the features according to their contribution in the coalition. Sounds reasonable, right? It's an interesting approach. Now, if you, the definition, and that's why I'm called this here, the fine print, don't read this too much because it makes your head hurt. But it's essentially about localized for every observation on an observation basis. Find the value of a feature as the average of the marginal contribution to all possible correlations. No questions, right? So there's a beautiful paper in Medium that's titled something like Sharp Values Explain. I wish to explain somebody to you. So here's what we're going through. Very simple model with 3 inputs. I want to predict someone's income from age, gender, and time in the job, right? There are 8 coalitions. That means configurations of players playing the game. Nobody might be playing 1 player, 2 players, or all 3 together. Now imagine I'm taking my data and I'm actually fitting 8 separate models. I'm going through the 2 to the P models and have 8 whatever predicted models. And I have an observation of interest. Tom, you're my target. And I'm gonna, no, I'm not gonna do this, Ellie. Some observation of interest, and I'm gonna predict that income under all 8 models. And these are the green numbers. These are the values I get. What I'm interested in is the marginal contribution of age. How do I do this? This is the Shapley calculation. So you imagine a model and then adding the feature of interest to it. So if I come from here, it's only this one. If I do this, my prediction goes from 50 to 40K, contribution of minus 10K. If I have a model which is gender and I add age to it, my prediction goes from 48 to 39K, down 9K. And I can do this for any model to which I can add gender, add age. And so these are all the green arrows. And then I compute the weighted average of those. And the weights are determined by how many links you have at each level, right? So I want them to add up to 1. So I'll take 1/3 of this, 1/6 of this, and so forth, and I add it up. And the contribution, the marginal contribution of age is minus $11,330. Now I go through, this is for 1 observation, 1 feature. Now I say, okay, what's the contribution of gender? Same exercise. I go here, and so forth. And I add, this comes out to be minus 2.33. And then finally, for the 3rd variable, it's 46.66. When you add those up, you get the difference between not playing the game, having no players, and all 3 playing. The difference is 33, 83 minus 50. That's the total payout. And this is how it gets distributed among the 3 players, age, gender, and time and job.
Quickly, how did you pick the 1/3, 1/6, 1/3? Was that arbitrary or is
No,
that some
it's-
way?
It's actually, if you look at how many connections are at each level, that's what the ratio is. Another way to look at it, there are twice as many connections going from a model with 1 to a model with 2 features. So this needs to have half the weight for this to come out to be, the weights to be equally distributed, the weights to sum to 1. So now you can do this for 1 observation. You can do this for all observation. In fact, if you then add them up, it actually is the global contribution to the entire model. So these have a local and a global interpretation. But in practice, we're not fitting 2 to the P model. We have 1 model, the one we're actually working with. So the baseline is not the model without players. The baseline is going to be the average prediction over the whole data. So I compare everybody to the average. That's the gain. We also have a lot of correlations. How do I evaluate this for every observation? Good grief. And that's where the computational complexity comes into play. So there are shortcuts, correlations are being sampled, observations are being sampled, values for features that are not a correlation, you just assign a random value to it. And so these are some of the shortcuts that actually drive the actual implementation of Shapley. But it's very easy to understand once you understand that concept of a Shapley value as distributing features, contributions to a prediction, or the difference of a prediction from the average. So in our bike example, this is for 1 particular day. It's observation by observation, day 285. The actual prediction was there would be 2,409 riders. The average across all time points was 4,518. So the difference is minus 2108. So now I'm distributing that difference among the features in a way that it adds up. So you can see humidity for that particular day is 90.625, has the largest negative effect, the largest negative Shapley value, pulls down the predictions. And temperature, which was moderate, helped bring it up. And so you see how every feature makes a contribution to the overall prediction. Rather than, in a surrogate model where you just have two features, everybody is being looked at. And it does have some really, really nice interpretation and visualization. This is from Molnar's book about a data set about predicting cervical cancer in women. This is called the Shapley force plot. Each feature, each effect has a force on the prediction. The baseline overall, so the average prediction is 0.066 rate of cervical cancer. For this particular subject, the prediction was close to the baseline at 0.06. And now in red, you see the variables that drive the prediction probability up, and in blue comes down. So for example, we're being relatively young compared to the cohort will reduce the prediction. On the other hand, for this particular subject, there's almost nothing in blue. All her attributes were pushing the prediction up, most largely being a smoker for 34 years. Very easy to understand, right? All in terms of features of the model. Shapley has its own version of variable importance. These are the basic questions: dependence, variable importance, impact on predictions. So what you do is you take the Shapley value, the absolute value, and you average it out. So like a feature can have some predictions can be positive and negative effect. This is just a sum of 12 absolute effects. Rank it, you get an idea of what features drive the predictions the most. You can combine this global view of feature importance with a local view on each individual. It's called a summary plot. In this plot, the color tells you whether a feature takes on a high value or a low value. Where you are, this axis is the importance of the feature. So if we see, for example, smoking, all the larger SHAP values are red. That means those are values where this feature has a higher value. So if you smoke a lot, it will push the prediction upwards. And it has its own form of a dependence plot that shows for each observation the variable, not against the prediction, but it's against its SHAP value, its force on the predicted value. And here's one from a specialized package. It's called SHAP for XGBoost. Works really well, works quite fast because it takes advantage of the tree structure of machines. This is I'm using this to predict column water vapor in satellite images. It contrasts them with the four most important variables against all the rest, and it allows you to zoom in and you understand exactly what's happening with these Shapley values. Beautiful visualizations. I think people tend towards this because of the, the achieve this of some of the visualizations that are coming out. But I think of all the explainability tools that I looked at, Shapley is the one I'm most comfortable with. It makes the least assumptions. It's grounded in game theory. It's easily recognizable. It's easily understandable. I don't have to select features to use to explain. It is non-sparse. It gives me information about everything. I can take a local model and I'll roll it up into a global interpretation. So all these things are really nice to have about the Shapley methods. There are others out there. There's counterfactual explanations, the technique. There are some that try to get around the issue of how features vary together. I think accumulated local explanation is one of those. I'm going to ask students in the class to work on some of these that we didn't cover as final projects and compare to some more frequently used methods. that is my overview to you of interpretability and explainability, and everything I know about the subject as if I had read it in a book, which I did.